Right now, as you are watching this, there are asteroids slipping past Earth that most people will never hear about. Not next month, not next year, this week. In a single 7-day stretch this year, roughly 8 different asteroids passed closer to Earth than the Moon itself. One of them, a rock the size of a house, came in closer than some of our own satellites, and it was only spotted days before it arrived. Car-sized objects thread this same gap almost every week. Bus-sized ones do it several times a year. Before modern telescopes existed, every single one of these would have zoomed by completely unnoticed. So the question that matters is simple. Is something changing out there? Are more asteroids actually heading toward us? Or are we just now switching on the lights and seeing what was always there? Today, we are going to break that down properly. No fear-mongering, no doomsday framing, just the real data, the detection numbers, and the real reason this feels like it is accelerating. Drop a comment right now. Did you know an asteroid passed closer to Earth than the Moon this week? Subscribe if you want to catch every close approach as it happens, completely free. Let us get into it. Let us start with what actually happened this year, because the numbers alone are enough to make anyone stop scrolling. In May 2026, an asteroid designated 2026 JH2 passed within about 56,900 miles of Earth. That is roughly a quarter of the distance to the Moon, closer than many of the satellites currently orbiting our planet. It was traveling fast, it was completely real, and it was discovered only days before it arrived. That same week, astronomers tracked approximately 8 separate objects passing inside the Moon's orbit. 8. In 7 days. Now rewind a few months earlier to February 2026, and you find a different kind of pattern. Not one dramatic close call, but a run of them, back to back, almost like clockwork. 2026 BX4, then 2026 AJ17, then 2026 CU, then 2026 CA2. 4 separate asteroids, 4 separate close approaches spread across consecutive days. If you were only half paying attention to space news that month, it would have looked like Earth was suddenly sitting in the middle of a shooting gallery. According to Dr. Richard Binzel, a planetary scientist at MIT, this is not actually rare. Car-sized asteroids pass through the gap between Earth and the Moon every single week. Bus-sized objects do the same several times a year. Before modern detection systems existed, every one of these would have sailed past in total silence. Nobody would have known. No alert, no headline, no tracking number. They simply would have come and gone. So when you stack these events together, 2026 JH2, the February run, the 8 objects in a single week, it creates a very specific feeling. It feels like the sky is getting busier. It feels like the frequency is increasing. It feels like something has shifted in how often these rocks are showing up in our neighborhood. And that feeling is not irrational. When you are the one watching the headlines pile up week after week, asteroid after asteroid, near miss after near miss, of course it looks like escalation. That is the honest, human reaction to the data as it appears on the surface. But here is where we need to slow down and ask the harder question. Because feeling like something is accelerating and something actually accelerating are 2 very different things. And to answer that properly, we need to go deeper than the headlines. We need to look at how many of these objects are actually out there, how many we are catching, and how that number has changed over time. Let us slow down and actually look closely at 2026 JH2, because this single object tells you almost everything you need to know about how modern asteroid tracking really works. This was not a massive, city-destroying rock. It was roughly the size of a house, somewhere in that car-to-bus category that shows up in the data constantly. But the distance is what made people pay attention. At around 56,900 miles from Earth, it passed closer than a quarter of the distance to the Moon. For context, that is closer than many geostationary satellites currently sitting in orbit above us right now. If this object had been on a slightly different trajectory, it would have been passing through the exact same neighborhood where our own infrastructure operates. Here is the part that should genuinely concern you, not because it means danger, but because it exposes a gap. 2026 JH2 was only discovered days before its closest approach. Not months, not years, days. And according to CNN's reporting at the time, that is because only about 1% of near-Earth asteroids in that particular size range have actually been catalogued and tracked. 99% of objects that size are still completely unknown to us, floating out there, waiting to be discovered the same way this one was, at the last possible moment. So think about what that actually means. This was not some rare failure of the system. This was the system working exactly the way it currently works for objects this size. We are not failing to detect these asteroids because something went wrong. We are failing to detect most of them because the tools required to catch that specific size range consistently, years in advance, are still being built. 2026 JH2 was a preview of that gap in real time. A rock the size of a house, passing closer than our satellites, arriving with only days of warning, and it was not even considered dangerous. That is the baseline reality we are currently living in. And once you understand that, the next question becomes obvious. If we are only catching a tiny fraction of objects this size, how many asteroids are actually out there in total? What does the full picture look like? And is that picture getting better or worse? Let us actually answer that question with real numbers instead of guessing. As of mid-2025, there were approximately 40,000 near-Earth objects catalogued and tracked by NASA and international observatories. That number is not static. It is growing by roughly 40 new discoveries every single week. Every week, 40 more rocks get added to the list of things humanity is now watching. Of those tracked objects, around 2,539 are classified as potentially hazardous asteroids as of May 2026, meaning their orbits bring them close enough to Earth and they are large enough that scientists keep a permanent eye on them. Of those, 153 are larger than 1 kilometer across, the size class capable of causing genuinely global consequences if one ever did strike. Now here is the number that should actually make you feel better, not worse. According to NASA's Jet Propulsion Laboratory Center for Near-Earth Object Studies, there is no known significant impact threat to Earth for the next 100 years or more. None. Back in 1998, the United States Congress issued a mandate to NASA: find 90% of all near-Earth objects larger than 1 kilometer. That goal has essentially been achieved. The objects capable of ending civilization, the ones that keep planetary defense scientists up at night, we have found almost all of them, and none of them are coming. So where does the anxiety actually come from? It comes from the smaller stuff. Scientists estimate there are still roughly 40 million near-Earth objects smaller than 30 meters across still waiting to be found. And only about 10% of the near-Earth asteroids we currently know about have been well characterized, meaning we understand their size, their composition, their exact trajectory in real detail. So the picture is not one of danger, it is one of incomplete information. We have solved the extinction level problem. What remains unsolved is the smaller, more common category, the house-sized and bus-sized rocks like 2026 JH2 that slip through because our detection systems were built to prioritize the biggest threats first. That raises the real question at the center of this entire video. If the asteroids have always been out there in these numbers, then what actually changed? Are more of them suddenly appearing? Or are we simply seeing what was always there? Here is the honest scientific answer, and it is the single most important sentence in this entire video. The number of asteroids near Earth is not increasing. Our ability to see them is. That is the whole story. Every single one of those objects we talked about, 2026 JH2, the February run, the 8-object week, they were not new arrivals to our neighborhood. Asteroids of that size have been drifting past Earth in roughly those same numbers for millions of years. Long before humans existed, long before we had telescopes, long before anyone was tracking anything, these rocks were already moving through this exact same gap between Earth and the Moon, week after week, completely unnoticed. What changed is not the sky. What changed is us. Specifically, what changed is our capacity to look up, detect something small and dark against a black background, calculate its trajectory within hours, and publish that data publicly for everyone to see. 30 years ago, an object like 2026 JH2 would have passed by in total silence. No alert, no article, no tracking number, nothing. It would have come and gone, and not a single person on Earth would have known it happened. Today, the same event generates headlines, because we finally have the instruments capable of catching it in time to say something. This is the exact same pattern we see over and over in science. When you build a better microscope, you do not create more bacteria, you simply reveal bacteria that were always there. When you build a better telescope, you do not create more asteroids, you simply reveal a solar system that was always this busy. So the real story here is not that space has become more dangerous. The real story is that humanity has gotten dramatically better at watching. And to understand exactly how much better, we need to look at how asteroid detection actually evolved to get us here. To understand why 2026 feels so different from, say, 1996, you need to understand what asteroid hunting actually looked like before modern surveys existed. For most of the 20th century, astronomers found asteroids by physically photographing the night sky on glass plates, then comparing those photographs by eye, night after night, looking for a single point of light that had moved position. It was slow, it was manual, it missed almost everything smaller than a mountain. That began changing sharply around 1998, the same year Congress issued its mandate to find the largest, most dangerous objects. Dedicated survey telescopes started coming online, purpose-built to scan the sky automatically, every single clear night, rather than waiting for a human astronomer to happen to look in the right direction at the right time. The Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, Atlas, also based in Hawaii, specifically designed to catch objects on a collision course, with days or weeks of warning. NASA's NEOWISE spacecraft, using infrared detection to spot asteroids that reflect almost no visible light but glow with heat. Each of these systems, one by one, multiplied the number of objects we could actually find. An asteroid the size of 2026 JH2 that slips through today with only days of warning would have slipped through entirely undetected a decade earlier. Not because the technology failed, because the technology to catch it simply did not exist yet. This is the actual explanation behind that growing number of 40,000 catalogued near-Earth objects and the 40 new discoveries added every single week. It is not that asteroids suddenly started showing up. It is that we built machines specifically designed to notice them, running continuously, every clear night, scanning the same sky that has always been this crowded. And in 2025, an entirely new machine came online, one that did not just improve on the old surveys, it made all of them look outdated almost overnight. This is where the story gets genuinely remarkable. The Vera C. Rubin Observatory, a massive new survey telescope built specifically to scan the entire visible sky repeatedly, began its early operations in 2025, and the results were staggering almost immediately. In one of its very first test runs, reportedly, the observatory detected over 2,000 previously unknown asteroids in roughly 10 hours of observation. 10 hours. That includes 7 brand new near-Earth objects, rocks whose existence nobody on this planet knew about until that single night. To put that into perspective, some individual astronomers spent entire careers discovering a few dozen asteroids total. This one telescope found thousands in less than half a day, and this is just the beginning of its mission. Over its planned 10-year survey, Rubin is projected to discover on the order of 127,000 near-Earth objects, along with millions of other solar system bodies, comets, distant asteroids, objects we currently have zero information about. It works by capturing the entire visible sky every few nights, comparing each new image against the last, and automatically flagging anything that moved. What used to take teams of astronomers weeks of manual comparison now happens through automated software in near real time. This is the moment asteroid detection stopped being a slow, careful process and became something closer to a factory line, constantly producing new discoveries night after night. So when you ask why it feels like more asteroids are showing up now than 5 years ago, this is your answer. It is not that space suddenly became busier. It is that we built a machine powerful enough to finally see how busy it always was. And Rubin is not finished. NASA has another instrument coming, one designed specifically to close the exact gap that let objects like 2026 JH2 sneak up on us with only days of warning. Now, let us be honest about where the real gap still exists, because pretending everything is solved would be dishonest. Small asteroids remain genuinely difficult to catch early. They are faint, they reflect very little light, and some approach from the sunward direction, hidden directly in the glare of the sun itself, making them essentially invisible until they are already close. This is exactly what happened with 2024 XA1, which blazed over Siberia in December 2024 and was detected only hours before it entered the atmosphere. It is what happened with 2024 BX1, the Berlin fireball, discovered roughly 3 hours before impact, with meteorite fragments recovered afterward. And it is what happened with 2026 JH2, found only days ahead of its close pass. This is not failure. This is the current limit of what our detection systems can do for objects in this specific size range. The clearest lesson in all of this is 2024 YR4. In February 2025, early observations showed a 3.1% chance this asteroid could strike Earth in 2032, the highest impact probability ever recorded for an object of its size. Headlines exploded, but as astronomers gathered more data, refining the orbit with each new observation, that probability collapsed entirely. Earth was ruled out. By early 2026, Even a secondary scenario involving a possible moon impact was ruled out as well. The lesson here matters more than the scare itself. Early impact odds almost always rise with uncertainty, then fall as better data comes in. That pattern is not concerning. It is science working exactly as intended, correcting itself in real time as the picture becomes clearer. So what happens if detection ever does reveal a genuine threat, not a 3% probability that later disappears, but a real, confirmed collision course? This is not hypothetical science fiction anymore. NASA has already tested a real solution. In 2022, the DART mission deliberately crashed a spacecraft into an asteroid called Dimorphos, successfully changing its orbit through simple kinetic impact. It worked exactly as predicted. Humanity has now proven, in actual practice, not theory, that we can physically alter the path of an asteroid. That is an enormous milestone in the history of our species. But here is the catch that makes early detection so critical. Deflection missions like DART take years to plan, build, and launch. You cannot discover a threatening asteroid next Tuesday and launch a spacecraft to intercept it next Wednesday. The entire defense strategy depends on finding dangerous objects a decade or more before they arrive, which is precisely why Rubin and the coming NEO Surveyor Space Telescope matter so much. NASA also runs 2 continuous monitoring systems working around the clock. Sentry tracks the orbits of every known asteroid, constantly recalculating impact probabilities as new data comes in. Exactly the process that ruled out 2024 YR4. Scout, meanwhile, watches brand new detections the moment they appear, screening for any object that might pose an imminent risk before it even receives a full orbital classification. Between Rubin finding the objects, NEO Surveyor closing the small asteroid gap, and Sentry and Scout monitoring everything in real time, the full defense system is finally coming together. Detection, confirmation, and if it's ever needed, a tested method to actually respond. So let us bring this back to the question we started with. Is something changing out there in space? No. Asteroids have been drifting past Earth in these exact numbers for millions of years, long before anyone was watching. What changed is us. We built telescopes powerful enough to finally notice what was always happening in our own neighborhood. Every close pass we talked about today, every crowded week, every last-minute discovery is a miss. Not a near disaster. A confirmed, completed miss. And every year, our ability to catch these objects earlier keeps improving. We are not being visited more often. We are simply awake enough now to notice. That is not a reason for fear. That is the safest position humanity has ever been in against this particular risk. We will keep tracking every new close approach as it happens, every discovery out of Rubin, every update from Sentry and Scout. Subscribe so you never miss one, and drop a comment below. Did any of these numbers surprise you? See you in the next one.